Light travels at a speed of about 299,792 kilometers per second. And if you're like most people, you think that's fast enough to get anywhere in the universe. But the truth is that intuition is completely wrong. Your brain isn't designed to understand distances like thousands of billions of kilometers. It's built to handle the distances you can travel in a day, not journeys that take years of light. And now let's ask a simple question. If the universe has about 100 billion galaxies, each containing hundreds of billions of stars, then why haven't we ever seen any definitive sign that an extraterrestrial civilization has reached Earth? You might think they just aren't advanced enough, but there's a much more concerning possibility. They can't get here, not because they lack the technology, but because the laws of physics themselves don't allow it. This isn't a story about intelligence or ambition, but about the limits of reality. And when you look closer, you'll realize that even light, the fastest thing we know, is too slow to solve this problem. To understand why this matters, you need to go back to the moment when humans first realized that light doesn't travel instantly, but has a finite measurable speed. In 1676, Olrömer observed the moon Io orbiting Jupiter, and noticed that the moment it disappeared behind the planet didn't happen exactly as predicted, but changed depending on the distance between Earth and Jupiter. And from that he deduced that light takes time to travel. This was the first time in history that we had evidence that light is not instantaneous, but has a specific speed. Nearly 2 centuries later, in 1865, James Clerk Maxwell described light as a form of electromagnetic wave in his equations, and from that he calculated its speed with astonishing accuracy. But the real turning point came in 1905, when Albert Einstein published his special theory of relativity, in which he didn't just treat the speed of light as a measurable number, but as a fundamental constant of the universe, independent of the observer or reference frame. This led to a profound consequence. No object with mass can reach, let alone exceed, that speed without requiring infinite energy. And this isn't an untested theoretical idea, because in modern experiments at CERN, particles are accelerated to near the speed of light but never surpass it, exactly as the theory predicts. So when you talk about traveling between the stars, you're not just talking about going faster. You're facing a boundary set by the very structure of space and time, a physical barrier for which to this day there is no evidence that it can be broken. If you want to see that this doesn't just exist in equations, but actually affects how the universe operates, then you need to start with a more familiar place, our solar system. Light from the sun takes about 8 minutes and 20 seconds to reach Earth, and that means every time you look up at the sky, you never see the sun as it exists right now, but always see it in the past, more than 8 minutes behind reality. This may sound insignificant, but it's the first example showing that even at distances we consider close, the speed of light is still not instantaneous. If the sun suddenly disappeared, you wouldn't know it for 8 minutes, and during that time, everything would continue as if nothing had happened. Now let's go a bit farther, to Mars, where the distance between it and Earth isn't fixed but changes according to the orbits of both planets, ranging from about 54 million kilometers at its closest to more than 401 million kilometers when they are on opposite sides of the sun. And this creates a very specific consequence. Radio signals, which are just light in another form, take from about 4 minutes to more than 24 minutes to travel one way between the two planets. That means you can't control a machine on Mars in real time, because when you send a command, you have to wait dozens of minutes to know what happened, and by then the situation has already changed. This isn't a hypothesis, but a real problem that NASA engineers have to deal with every day. And that's why rovers like Perseverance aren't driven like a remote-controlled car, but operate semi-autonomously, analyzing their environment and making decisions in many situations. When you expand farther out to the gas giant planets like Jupiter, you start to see the delay become even clearer, because the light signal traveling back and forth between Earth and Jupiter can take about 43 minutes, meaning nearly an hour passes between the time you send a command and the time you receive a response. At this point, the concept of control almost disappears and is replaced by plan ahead and hope everything goes right. But what really makes you realize the scale of the problem is when you look at the farthest objects we've ever sent, like Voyager 1, launched in 1977 and now more than 24 billion kilometers from Earth, equivalent to more than 160 astronomical units. And at that distance, its radio signal takes more than 22 hours to reach Earth. This means that when you receive data from Voyager 1, you're actually looking at the past nearly a day earlier. And if you send a command back, you'll have to wait nearly 2 days to see the result. And note that Voyager 1 still hasn't completely left the sun's sphere of influence. It has only just entered the near-interstellar environment, an area that in cosmic terms is still considered our backyard. When you put all these numbers together, from 8 minutes to the sun, to dozens of minutes to Mars, nearly an hour to Jupiter, and nearly a day to Voyager 1, you begin to see a very clear pattern. The speed of light is not instantaneous at all, and this delay increases rapidly with distance. And the important thing is that all of this is still happening in an extremely small region of space, compared to the distances between the stars, where light no longer takes minutes or hours, but years, tens of years, or even thousands of years to travel. So before you think about going to another star system, you need to accept a simple but counterintuitive reality. Even in our own solar system, the speed of light is already a clear operational limit, a factor that determines how we communicate, control, and understand the universe. And if it already creates barriers at such small scales, then when expanded to interstellar scales, it is no longer just a limit, but becomes a wall that is almost impossible to overcome. And when you leave that backyard to look beyond the stars, everything starts to change in a way that your intuition can barely keep up with. The closest star to us, Proxima Centauri, is about 4.24 light years from Earth. And that means even light, the fastest thing in the universe, takes more than 4 years to travel from there to here. If you convert that number into more familiar units, it's equivalent to about 40 trillion kilometers, or 40,000 kilometers. A number so large that trying to imagine it is almost meaningless to the human brain. To give you a clearer sense, try another way. If you drive a car at 100 kilometers per hour without stopping or resting, it would take you more than 45 million years to reach that nearest star, a time far longer than the entire history of modern humans. And even if you don't use a car, but one of the fastest objects we've ever built, like the Voyager 1 spacecraft, which is currently traveling at about 17 kilometers per second, or more than 60,000 kilometers per hour, you would still need more than 70,000 years to reach Proxima Centauri. Not 70 years, not 700 years, but 70,000 years. A period long enough for our entire current civilization to appear, develop, and disappear many times over. And this is just the distance to a neighboring star, a point right next to us on the cosmic scale. When you expand farther out, you begin to see the true scale of the problem, because the galaxy we live in, the Milky Way, has a diameter of about 100,000 light years, meaning light needs 100,000 years to travel from one end to the other. And that means even if you could travel at the speed of light, you would still need a period longer than the entire history of human evolution to cross your own galaxy. And remember that we are not at the edge of the galaxy, but somewhere in a spiral arm about 27,000 light years from the center, meaning that even traveling from our current position to the galactic center is a journey spanning tens of thousands of light years. But it doesn't stop there, because when you look beyond our own galaxy, you begin to see distances that are much larger still, like the Andromeda galaxy, the nearest large galaxy to us, which is about 2.5 million light years from Earth, meaning the light you see from it today actually left before modern humans appeared on Earth, before the first civilizations formed, even before many modern animal species evolved. If you try to think about going there, even at the speed of light, you're talking about a journey lasting 2.5 million years, a time longer than the entire history of humanity by dozens of times. And if you're slower than light, even by a little, that time would stretch even longer, quickly becoming millions or tens of millions of years. At this point, the issue is no longer speed, but distance, because even if you reach the maximum limit that physics allows, you are still facing distances measured in periods of time longer than anything a civilization could maintain. And this is exactly what most people overlook when they think about interstellar travel. They focus on going faster, building better engines, searching for more advanced technology, but they don't realize that before you talk about speed, you have to face the reality that the universe is simply too big. Distance is not just a secondary factor in this equation. It is the dominant factor, because when the distance is large enough, even the maximum speed becomes insufficient. And when you put all of this together, from a few light years to hundreds of thousands of light years to millions of light years, you begin to see a much clearer picture. The biggest barrier for any civilization is not how fast they can go, but how far they have to go. And in a universe where distances are measured in times longer than their own history, getting there may no longer be a realistic option, but becomes something that is almost impossible to achieve. And if you start to feel that these numbers are exceeding your ability to imagine them, that's not your fault. It's the way your brain is designed. The human brain evolved to understand a very specific environment, the surface of Earth, where distances are measured in meters, kilometers, or at most a few thousand kilometers. And time is measured in seconds, minutes, and days, not in light years or millions of years. You can imagine a 10-kilometer road. You can picture a flight lasting a few hours. But when you start talking about thousands of billions of kilometers, or periods of tens of thousands of years, your intuition simply stops working. To see this clearly, go back to a number you think is familiar. Light travels about 300,000 kilometers in 1 second, meaning in the blink of an eye it can circle the Earth more than 7 times. And that sounds extremely fast, almost unimaginable. But then you put that number next to another reality. Light takes more than 4 years to travel from Proxima Centauri to Earth. And suddenly fast no longer means what you thought it did. The same speed, the same rules, but when the distance changes, your perception of speed completely collapses. This is the point where your intuition betrays you, because it was built to handle linear changes, not enormous differences in scale. When you hear that something travels 300,000 kilometers per second, you automatically label it almost instantaneous. But in reality, instantaneous only holds within the range you're familiar with. When you expand to cosmic scales, that same speed becomes astonishingly slow. This is like watching an ant moving on a table and thinking it's very slow. But if you shrink the entire world down to the size of the ant, its speed becomes significant. And conversely, if you scale the distance up to cosmic proportions, even light becomes sluggish. The problem here isn't that we lack information, but that we have too much information beyond what our intuition can process. You may know that the distance to the nearest star is 4.24 light years. You may know that 1 light year is about 9.46 trillion kilometers. But knowing these numbers doesn't mean you understand them. Understanding here isn't just remembering the numbers, but feeling their meaning. And that's exactly what your brain can't do. When you try to visualize such a distance, you unconsciously shrink it down to something more familiar. And that very shrinking causes you to misjudge the entire problem. This is why so many people think that if we had better technology, we could just go a little faster and reach the stars, because they're applying the intuition of Earth travel to a completely different context. But the universe doesn't work that way, and the rules you're familiar with don't simply scale up when you change the magnitude. The gap between 300,000 kilometers per second and 40 trillion kilometers isn't just a difference in quantity, but a difference in kind, a difference large enough to break every ordinary way of thinking. And when your intuition breaks down, you start relying on feeling instead of logic, and that's when you begin to believe that things like interstellar travel just require more time and technology. But when you look at the numbers seriously, you realize that the problem isn't that we aren't fast enough, but that we're misjudging the scale of the problem from the very beginning. And this is the most important point, because if you misunderstand the scale, you'll misunderstand the possibilities. You'll think there's a realistic path from here to there, when in reality the distance between those 2 points has already exceeded everything you can handle. So before you talk about engines, fuel, or technology, you need to correct the way you look at the world, because the universe isn't wrong. The numbers aren't wrong. Only our intuition can't keep up. And when you start looking at everything through the lens of the real numbers, you'll see that the limits don't lie in what we haven't achieved yet, but in what cannot be done in the first place. And when you have realized that your intuition is unreliable at this scale, the next step is to face an even harsher reality, that even if you understand the scale correctly, you still cannot overcome it, because there is a fundamental limit that the universe imposes on everything. According to the theory of relativity, no object with mass can reach or exceed the speed of light, and this is not an assumption or a temporary technological limit, but a direct consequence of the way space and time are structured. When you start accelerating an object, everything seems normal at low speeds, just like the way you drive a car or fly on an airplane. But when you approach the speed of light, effects begin to appear in ways you cannot ignore. Time for that object begins to slow down compared to an outside observer, and space in the direction of motion begins to contract. This is not a magic trick or a purely mathematical interpretation, but a real physical phenomenon that has been measured. Fundamental particles in nature, when accelerated to very high speeds, live longer than in their rest state, because time passes more slowly for them. And this has been confirmed in many different experiments. The clearest example is in particle accelerators at CERN, where protons are accelerated to 99.999% of the speed of light. And at that speed, relativistic effects are no longer minor details, but become the dominant factor in the entire behavior of the system. But what is more important is that no matter how much energy you provide, these particles never reach the speed of light. They only get closer and closer, like approaching a wall without ever touching it. The reason is that as velocity increases, the energy required to increase the velocity a little more does not increase linearly, but increases in an increasingly steep way, approaching infinity as you approach the speed of light. You might think that increasing from 10% to 20% of the speed of light would be similar to increasing from 80% to 90%, but the reality is completely different, because in the region near the speed of light, each additional percentage requires a vastly greater amount of energy than before. That means that to push an object with mass up to exactly the speed of light, you would need an infinite amount of energy. And infinite here is not a figure of speech, but a specific mathematical result from the equations describing relativistic motion. And this is the point where you need to stop and think, because if something requires infinite energy, then it is not just difficult, but impossible in any real universe. This also means there is no such thing as just needing better technology to overcome this limit, because you cannot build a machine that produces infinite energy, not because we are not smart enough, but because the concept itself contradicts the laws of energy conservation. Even the smallest particles in nature, the easiest things we know to accelerate, cannot overcome this limit, and if they cannot do it, then a ship weighing thousands of tons, carrying humans, life support systems, fuel, and everything else, has even less chance. This turns the speed of light from an impressive number into an absolute boundary, a line that you can approach but never cross. And when you place this limit next to the distances we just talked about, you begin to see the real problem clearly. Because if you cannot travel faster than a certain speed, and the distances are unimaginably large, then the problem is no longer how to go faster, but whether going there makes any sense at all. You can imagine a ship that can reach 90% of the speed of light, and that sounds impressive, but even at that speed, Traveling to the nearest star would still take more than 4 years according to an outside reference frame. And if you want to go farther, into deeper regions of the galaxy, you are still talking about thousands of years. And if you are slower, only 10% or 1% of the speed of light, then that time quickly increases to tens of thousands or hundreds of thousands of years, far beyond the survival capability of any technical system we can imagine. This is not an open question in modern science, but a conclusion that has been reinforced by centuries of observation and experimentation, from the first measurements of light to the most advanced particle accelerators of today. So when you think about an extraterrestrial civilization flying to Earth from another star system, you are not just imagining a faster ship, but assuming they can overcome a limit that the very structure of the universe has set. And so far, there is no evidence that this is feasible. And when you understand this fully, you begin to realize that the speed of light is not just a number in a textbook, but a fundamental law, an absolute limit that everything in the universe, from the smallest particles to the greatest ambitions of any civilization, must obey. The point where most people begin to realize the problem is not in the speed itself, but in the price that must be paid to achieve that speed, appears when you look at a very simple but extremely profound equation of Albert Einstein, E = mc squared. This equation tells you that energy and mass are not two separate things, but two forms of the same entity. And when you try to accelerate an object, you are not just making it move faster, but you are pumping energy into its very structure. At low speeds, this is insignificant, but when you approach the speed of light, everything begins to change in a counterintuitive way, because the energy required to increase the velocity a little more does not increase evenly, but increases along an increasingly steep curve, to the point where each additional percentage near the speed of light requires more energy than everything you used before combined. If you try to push a ship to 10% of the speed of light, that is already a huge challenge, but still within the imaginable range. But when you try to go from 90% to 99%, or from 99% to 99.9%, the amount of energy required does not just double or triple, but increases exponentially, quickly approaching a value you cannot supply. This means that to reach exactly the speed of light, you would need an infinite amount of energy, and that is not a figure of speech, but a direct result from the relativistic equations. You can imagine this with a simpler example. Suppose you have a ship weighing 1,000 tons, and you want to accelerate it to a significant fraction of the speed of light. The energy required would be equivalent to the energy that all of humanity produces in many years, even decades. The total annual energy consumption of the entire world today is about 6 × 10^20 joules, and that number sounds large, but when you place it next to the energy needed to accelerate a large object to near the speed of light, it becomes astonishingly small. And that is just to reach that speed, not counting the additional energy needed to stop when you arrive, or to maintain the life support systems throughout the journey. When you add all of this together, you begin to see that the problem is not just how to build an engine powerful enough, but whether there exists any energy source in the universe that you can harness to achieve it. Even if you imagine that a civilization far more advanced than us could harness the entire energy output of a star, something sometimes called a Type 2 civilization on the Kardashev scale, they would still face the same problem. Because as you approach the speed of light, the energy requirement is not just large, but approaches infinity, meaning no level of technological progress can help you cross that point. This completely changes the way you should think about interstellar travel, because it is no longer a technical problem that you can solve with time and creativity, but becomes a problem locked by the laws of physics themselves. You can build better engines, more efficient fuel, or more optimized systems, but all those improvements only help you get closer to the limit, not help you surpass it. And when you place this in the context of the distances we talked about earlier, from tens of trillions of kilometers to millions of light years, you begin to see that not only is going fast difficult, but having enough energy to go fast is also nearly impossible. This is why when you hear someone say that an advanced enough civilization could easily travel between the stars, you need to stop and ask a simple question. Where does that energy come from? Because if the answer cannot be explained within the framework of current physics, then it is not a realistic plan, but only an assumption. When you understand this, you begin to see that the equation E = mc squared is not just a famous symbol of science, but a very specific reminder that every motion, every acceleration, every effort to cross distances in the universe must be paid for with energy, and that price increases much faster than your intuition expects. And at some point, that price is not just large, but impossible to pay, not because we are not developed enough, but because the universe does not allow it to happen. Another direct consequence of what has just been said, and also one of the least intuitive things in the entire story, is the concept of relativistic mass. When you look at an object at rest, you can assign it a fixed mass, a clear number. But when that object begins to move at very high speed, especially when approaching the speed of light, the way it interacts with energy and force begins to change. According to the theory of relativity, as velocity increases, the momentum of the object no longer increases linearly, as in classical mechanics, but increases faster than expected. And this can be understood intuitively as the object becoming heavier as it moves faster. What is important here is not that the rest mass of the object changes, but that the way it responds to force and energy makes it behave as if it has greater mass. When you try to accelerate it further, you have to push something that is increasingly hard to push, like trying to accelerate a car, but every time you press the gas, the car immediately becomes heavier. At low speeds, this difference is very small and almost insignificant, which is why in everyday life you never notice it. But when you approach the speed of light, this effect becomes overwhelming. An object moving at 90% of the speed of light will have a much larger effective mass than when it is at rest. And when you push it to 99%, that number increases even more strongly, not additively, but according to a very steep nonlinear function. This means that each step toward the speed of light not only requires additional energy, but also requires you to overcome an increasingly large inertia, as if you are climbing a hill whose slope keeps increasing. This is exactly where everything starts to lock into a loop. To accelerate, you need energy, but as you accelerate, the object becomes heavier, and as it gets heavier, you need even more energy to continue accelerating. This loop has no natural stopping point. It only gets worse as you approach the speed of light, and ultimately converges to a point where the energy requirement approaches infinity. This is not a minor detail or a small effect that can be ignored, but one of the main mechanisms that makes the speed of light an uncrossable limit. Even in modern experiments, where we accelerate particles to extremely high speeds, we still see this effect clearly, because the faster you try to push, the more energy is needed for each small step, and the benefit you receive gradually diminishes. This is like trying to run faster and faster, but each time you accelerate, you have to carry additional weight, making each step harder than the previous one. When you place this in the context of a real spacecraft, with a mass of hundreds or thousands of tons, the problem becomes much more serious, because you are not just accelerating a small object in a laboratory, but an enormous system with fuel, structure, and humans inside. And as the effective mass of that system increases with velocity, you quickly reach a point where every additional acceleration effort becomes meaningless, because the energy required to overcome that new heaviness far exceeds any energy source you can provide. This is exactly why saying we just need a stronger engine is a wrong way to look at the problem, because the problem is not in the engine, but in the nature of motion at high speeds. You cannot design a system that escapes this loop, because that loop is built into the laws of physics themselves. And when you combine this with what we have said about energy and distance, you begin to see a consistent picture emerge. The faster you try to go, the more you are pulled back by the very rules that allow you to move in the first place. This is not a soft limit that you can push a little farther, but a hard limit, where every path leads to the same result. So when you think about accelerating a ship to a speed large enough to cross the distances between the stars, you are not only facing an energy problem, but also facing a self-amplifying loop, where each step forward makes the next step disproportionately harder. One of the ideas that makes many people believe there is still a way out from all these limits is the phenomenon of time dilation, a direct consequence of the theory of relativity. And at first glance, it really does seem like a way to overcome distance. When an object moves at very high speed, especially near the speed of light, time for it passes more slowly than for a stationary observer. And this is not speculation, but has been verified by many specific experiments. A classic example is the Havlik-Keating experiment in 1971, in which scientists placed atomic clocks on airplanes flying around Earth. And when compared with clocks on the ground, they found a time difference exactly as predicted by the theory. On a smaller but clearer scale, muons generated from cosmic rays in the atmosphere have a very short lifetime of only about 2.2 microseconds when at rest. But because they travel near the speed of light, time for them is stretched, allowing them to exist longer and reach Earth's surface, something that according to classical mechanics should not happen. This evidence shows that time dilation is a real phenomenon. And from that, an appealing idea emerges. If you put an astronaut on a ship moving at extremely high speed, then for that person the journey could be much shorter than what outside observers see. For example, if you could travel at about 99.5% of the speed of light, then a trip to Proxima Centauri might take only a few years on the astronaut's clock, while for Earth more than 4 years would still pass. And if you go even faster, this effect becomes even more pronounced. This creates the feeling that you can cheat distance, that you don't need to wait tens or hundreds of years to arrive, because your time passes more slowly. But the problem is that you are only changing the way you experience time, not changing the distance itself or the time of the universe. The person on the ship may feel the journey is short, but for everything outside, including the destination, time still passes normally. That means when the astronaut arrives, they may have aged only a few years, but the planet they reach has experienced tens or hundreds of years, and if the journey is longer, this difference can reach thousands of years. And if you think about an extraterrestrial civilization coming to Earth, then you have to look from our perspective, not theirs. No matter how they experience the journey, we still have to wait the entire amount of time for them to appear. And if that time span is thousands or millions of years, then in practical terms it is no different from them never arriving. This also means that time dilation does not help solve the communication problem, because signals are still limited by the speed of light, and all information still takes the same amount of time to travel between 2 points. And more importantly, to achieve significant time dilation, you have to return to the old problem. You need to travel at a velocity extremely close to the speed of light, which we have already seen requires nearly infinite energy and is limited by the relativistic mass effect. This creates a familiar loop, where the solution seems to exist, but to achieve that solution you must overcome the very barriers it cannot break. You can make your own time pass more slowly, but you cannot make the universe wait for you, and that is the key point. Therefore, although time dilation is a real phenomenon, measured and confirmed with high precision throughout the 20th century, it is not a way out of the interstellar travel problem, but only another way to see more clearly how tightly bound that problem is. It does not make the distance physically shorter, does not make light faster, and does not change the reality that every journey must still obey the same limit. When you place it in the overall picture, you begin to realize that no single effect can save you from these limits, because they are all interconnected and all lead to the same unavoidable conclusion. You can make the journey seem shorter for yourself, but you cannot make it actually shorter for the universe. A very natural reaction when you hear about all these limits is to look for a shortcut, some way to not have to obey the rules just described. And that is when ideas like warp drive or wormhole come into the conversation. You may have heard about the Alcubierre drive, a model proposed in 1994 by physicist Miguel Alcubierre, in which space in front of a ship is contracted and space behind it is expanded, allowing the ship to move faster than light in a geometric sense, without directly violating the local limit of relativity. On paper, this equation has solutions, and mathematically it looks very appealing. But when you start asking the more important question, what is needed to make it work, the problem appears immediately. Initial calculations showed that you would need a negative energy equivalent to the mass of an entire planet like Jupiter, and not just ordinary energy, but negative energy, a form of matter never observed on a large scale in nature. Later improved versions reduced the energy requirement, but it still remains far beyond any realistic capability. And more importantly, there is no experimental evidence that you can create or control this form of energy in the necessary way. Another idea often mentioned is the wormhole, a concept that emerged from solutions to Einstein's equations in 1935 in the work of Albert Einstein and Nathan Rosen, in which two distant points in spacetime are connected by a tunnel. If they exist, wormholes could allow you to go from point A to point B without traveling the distance between them in the usual way. And that sounds like the perfect solution to the interstellar travel problem. But once again, when you move from the equation to reality, the problem becomes clear. To keep a wormhole open, you also need a form of exotic matter with negative energy, and there is no evidence that it exists in a usable form. Even if wormholes exist naturally, they could be extremely unstable, collapsing immediately before anything could pass through. In addition, many models show that using wormholes could lead to causality paradoxes, where you could create time loops, something many physicists believe is forbidden by deeper principles of the universe. When you look at all of this, you begin to see a familiar pattern. Every solution seems to promise a way past the limits, but all require conditions that we have not only not achieved, but may be impossible to achieve. There has been no experiment at CERN or any other laboratory that has ever created a stable warp bubble or wormhole. No astronomical observation has confirmed their existence in a usable form, and there is no complete theory that integrates them consistently with all known physical laws. This does not mean these ideas are worthless, because they help us explore the boundaries of current theories and raise important questions, but they are not technical solutions you can rely on to solve a real problem. The difference between a mathematical idea and a feasible technology is very large, and in this case that gap may never be narrowed. So when you hear that an advanced enough civilization could use warp drive or wormhole to reach Earth, you need to realize that you are hearing about unproven hypotheses, not proven technologies. And when you remove these assumptions, you return to what we actually know, what has been measured, verified, and repeated. And all of that points to the same conclusion. With current physics, there is no shortcut, no secret passage through space, and every journey must obey the same limit we have seen from the beginning. When talking about interstellar travel, but decisive in nature, is the fact that space itself is not empty, as you usually imagine. Between the stars exists an environment called the interstellar medium, containing dust and gas particles, ranging in size from micrometers to millimeters. And although their density is very low, only about a few atoms per cubic centimeter, they are still enough to become a serious hazard when you travel at extremely high speed. At ordinary speeds, these particles are almost insignificant. But when you approach the speed of light, everything changes completely, because collision energy does not increase linearly with velocity, but increases with the square of the velocity. And in the relativistic regime, it increases even faster. To give you a concrete picture, take a small dust particle with a mass of about 1 milligram, and suppose it collides with a ship moving at 0.1 times the speed of light, or about 30,000 kilometers per second. The kinetic energy of that collision would be about 4.5 × 10⁸ joules, equivalent to more than 100 kg of TNT explosive, or on the scale of a small industrial explosion. and that is only at 0.1 c. If you increase the speed to 0.5 c or 0.9 c, the collision energy does not just increase by a few times, but by tens or hundreds of times, because relativistic effects begin to dominate. This means that a tiny dust particle you cannot even see can carry energy equivalent to a cannon shell, or even more upon impact. In practice, current spacecraft, like those in the Apollo program or NASA probes, have had to be designed with micrometeoroid shielding to protect against small particles moving at a few tens of kilometers per second. But those shields are completely insufficient if you increase the speed to tens of thousands of kilometers per second. On an interstellar scale, you cannot simply armor your ship, because to withstand collisions carrying hundreds of megajoules of energy, you would need a protective layer so thick that it would greatly increase the ship's mass. And that brings us back to the energy problem we discussed earlier. This is another loop where every solution creates a new problem. It is not only dust, but also charged particles in the interstellar medium. And when you move fast, they form a continuous radiation stream bombarding the ship from the front, like plunging into a rain of extremely high energy particles. Studies from the 1970s to the present, including models by physicists such as Robert Forward, have shown that at relativistic speeds, the front of a ship would have to withstand an amount of collision energy enough to melt or destroy materials in a short time if there is no extremely special protection. And even if you could design a high-energy shielding system, you would still face the reality that these collisions are not rare events, but a continuous process throughout the journey, meaning the ship would be gradually eroded over time. When you extend this journey over years or tens of years, the total energy the ship must absorb becomes enormous. This leads to a very direct conclusion. You not only need energy to accelerate the ship, but also need energy to protect it from the environment it is traveling through. And these two requirements together push the problem far beyond realistic capability. So when you imagine a ship racing through space at near light speed, you should not think of an empty and quiet environment, but of a journey through an invisible minefield, where every small particle can become an explosion, and the number of those mines is enough to turn the journey into a continuous battle with the surrounding environment. This is not a minor detail that can be ignored, but one of the direct and unavoidable physical barriers, because it does not depend on your technology, but on the reality that space, however empty it may look, still contains enough matter to become dangerous when you move fast enough. Interstellar space not only contains dust, but is also permeated by a continuous stream of high-energy radiation called cosmic rays, consisting mainly of protons, electrons, and heavy ions, such as iron nuclei. And these particles can carry energies up to giga-electron volts, and in some rare cases, even tera-electron volts. In a static state, that is, when you are not moving at too high a speed, this radiation is already dangerous enough, because it has the ability to penetrate matter and cause ionization, breaking molecular structures and damaging DNA. This is why astronauts on the International Space Station, operating at an altitude of about 400 kilometers above Earth, receive a much higher radiation dose than people on the ground, averaging about 80 to 160 millisieverts per year, compared to about 2 to 3 millisieverts that an average person receives from the natural environment. But when you start moving at high speed, especially a significant fraction of the speed of light, the situation changes in a much more dangerous way. Due to the relativistic Doppler effect, radiation particles coming from the front of the ship will be compressed in terms of energy, meaning their energy in the ship's reference frame increases significantly. A proton with energy of a few GeV in space may appear as a particle with much higher energy when colliding with a fast-moving ship, and this turns a relatively weak radiation stream into an extremely dangerous wall of radiation in front. This not only increases the level of ionization, but also increases the penetrating power of the particles, allowing them to pass through physical shielding more easily. In such an environment, Protecting humans becomes an extremely large challenge, because to block high-energy particles, you need very thick materials, usually heavy metals or water. But adding this mass again increases the ship's weight, returning to the energy problem we saw earlier. Even worse, when high-energy particles collide with the shielding, they can produce secondary radiation, including neutrons and gamma rays, making the environment inside the ship more dangerous instead of safer. Studies from agencies such as NASA and ESA have shown that even in long-term missions to Mars, controlling radiation dose has already been a major problem, and that is at speeds very low compared to the speed of light. When you move to relativistic speeds, this problem not only increases but also changes in nature, because you are no longer dealing only with a static radiation environment, but with a stream of high-energy particles amplified by your own motion. This means you cannot simply shield in the usual way, because the source of danger is not fixed, but depends on your speed. The faster you go, the stronger the radiation in front becomes, creating a situation where the solution makes the problem worse. And when you extend this journey over years or decades, the total radiation dose that the ship and crew must endure will far exceed any safety limits we know. Even electronic systems will be affected, with single events like bit flips causing system errors, and at higher levels possibly leading to complete failure. When you combine all these factors, you begin to see that radiation is not just an additional risk, but a direct physical barrier to high-speed travel. It is not something you can eliminate completely, but only mitigate, and as speed increases, that mitigation capability becomes increasingly limited. Therefore, even if you solve the problems of energy, mass, and collisions, you still have to face an increasingly harsh radiation environment, where complete protection becomes almost impossible, not because we lack sufficient technology, but because the laws of physics combine in a way that makes every step forward come with an ever-increasing price. Navigation in space may sound simple when you imagine it as an empty map with a few marked points, but in reality, it is an extremely precise problem based on reference points like the positions of stars, radio signals, and inertial reference systems, and all of these depend on measurement and adjustment over time. When the distance is still small, as within the solar system, you can still correct the trajectory by sending signals back and forth, using systems like NASA's Deep Space Network to determine the spacecraft's position with high accuracy. But as the distance increases, signal delay begins to become the dominant factor, because every time you send a correction command, you have to wait minutes, hours, or even days to know the result, and by then the spacecraft has already traveled a significant additional distance. This means every adjustment is based on outdated information, and in a system that requires extremely high precision, that is a serious problem. To see clearly how sensitive this problem is, consider that an angular error of just a few microradians, that is, about 1/1,000,000th of a radians, can lead to a deviation of millions of kilometers when you travel interstellar distances. For example, if you are off course by only 1 microradian over a distance of 1 light year, you will miss the target by about 10 billion kilometers, a distance greater than Pluto's orbit. This means you cannot just go roughly in the right direction, but must go almost perfectly accurate right from the start. Probes like Voyager 1 and Voyager 2, launched in 1977, are proof of humanity's extremely precise navigation capability. But remember that they are still operating within the solar system and are continuously supported by signals from Earth. Even under those conditions, their trajectory corrections still had to be calculated with extremely high precision, and any deviation needed to be corrected in a relatively short time. When you expand this problem to interstellar scale, everything becomes exponentially harder, because you not only lose the ability to make quick adjustments, but also lose the ability to determine your position accurately in an environment where reference points become weaker and harder to measure. The stars you use for positioning are also moving, and the light from them arrives with large delays, meaning you are always working with a map of the past of the universe. This creates a system in which errors not only exist, but also accumulate over time, and there is no effective correction mechanism to eliminate them. When you combine this with high speed, where every second that passes equals tens of thousands of kilometers of travel, a small initial error quickly becomes a large deviation that you cannot correct. This is not just a technical problem that can be solved with better computers or more precise sensors, but a consequence of trying to navigate in an enormous space with delayed and imperfect information. And when you extend this journey over years or decades, every error, no matter how small, has time to develop into a large deviation. The result is that you may start the journey with an almost perfect trajectory, but just a small error in measurement or execution can cause your spacecraft to miss the target by millions or billions of kilometers. And at that distance, turning back or correcting is almost impossible, especially when you have no external support system. This leads to a very clear but hard to accept conclusion. In interstellar travel, you not only have to go fast enough and long enough, but you also have to go almost perfectly accurate right from the beginning. And in a system where information is always delayed and the environment is constantly changing, achieving that level of precision may not just be difficult, but unfeasible. Time begins to dominate the entire problem as soon as you attach specific numbers to distance and speed, because even in an optimistic scenario where you can reach 10% of the speed of light, that is about 30,000 kilometers per second, a journey to Proxima Centauri would still take more than 40 years, according to an outside reference frame, and that is under ideal conditions, not counting acceleration, deceleration, or any delays. 40 years is no longer an abstract number. It is a period long enough for a human to go through nearly their entire adult life. And if you increase the distance to farther star systems or other regions of the galaxy, that number quickly becomes hundreds or thousands of years. And the important thing is that 10% of the speed of light is not something we can achieve with current technology, but an extremely optimistic assumption. With what we have today, the fastest spacecraft like Voyager 1 only reach about 17 kilometers per second, which is about 0.00006% of the speed of light. And at that speed, the journey to Proxima Centauri would take more than 70,000 years, a period longer than the entire history of human civilization, from the first civilizations in Mesopotamia to the present. When you start talking about time spans like that, you are no longer talking about a mission, but about a process stretching across many generations, even thousands of generations, if the speed is low enough. This leads to a completely different problem, no longer physics or engineering, but social and biological, because you need to maintain a human community in a closed system for hundreds or thousands of years. The idea of generation ships has been discussed for many decades, where the descendants of those who set out would be the ones to arrive at the destination. But this raises a very difficult question: how to ensure that the original goal is maintained across many generations. Human history shows that even in stable societies, goals and values can change significantly in just a few centuries, let alone thousands of years. A mission set today may no longer make sense to the people living on the ship after a few hundred years, especially when they have no direct connection to the destination or to Earth. Even the concept of a destination may become vague, distorted, or replaced by new priorities of that community. And even if you assume that a civilization can maintain discipline and goals over such a long time, you still have to face the problem of system durability, because no machine is designed to operate perfectly for thousands of years without external support. Every system has a failure probability, and when you extend the time long enough, that probability approaches 1, meaning failure is inevitable. You cannot send a repair team, you cannot replace parts from outside, and you cannot go back and start over. This turns time from a simple variable into a factor that amplifies every other risk we have discussed earlier, from radiation and collisions to navigation errors. Each year that passes is not just 1 year closer to the goal, but 1 year that increases the chance of failure. And when you extend that to tens of thousands of years, you are no longer talking about small probabilities, but near certainty that something will happen. This is why time is not just a number in the equation, but a systemic barrier, because it connects with every other factor and amplifies them. You may imagine that with enough technology, you can solve each problem individually. But when time is long enough, all those problems come back and accumulate. And this is the most important point. Interstellar travel does not only require you to cross distance, but requires you to maintain a stable system over a period longer than any system we have ever built, or even observed. When you put all of this together, you begin to see that time is not just an additional barrier, but the factor that turns a difficult problem into one that is almost impossible, because it not only adds difficulty, but also worsens every other limit we have seen from the beginning. A direct consequence of everything just said is the absolute isolation that an interstellar ship must face as soon as it leaves the solar system's range, because from that moment on, it is no longer in any support network, with no refueling stations, no repair facilities, no rescue teams, and no form of infrastructure we are familiar with on Earth, or even in nearby orbit. Even the farthest missions humans have ever carried out, like the Voyager spacecraft launched in 1977, still rely on communication with Earth through NASA's Deep Space Network. And although their signals take hours to arrive, they are still within the range where humans can monitor and send correction commands. But when you go farther, to interstellar distances, signal transmission time is no longer minutes or hours, but years. Meaning if a ship encounters a problem, its distress signal may take many years to reach Earth, and the response back will take many more years, making the entire process meaningless in practical terms. This turns every error, no matter how small, into a serious problem, because there is no way to make remote repairs in a useful time frame. Imagine a life support system on the ship that maintains pressure, temperature, oxygen, and water for the crew. If a valve fails, a sensor malfunctions, or software glitches, you cannot call an engineer from Earth to fix it. You cannot order a replacement part, and you cannot shut the system down and wait for later repairs, because human life depends on it operating continuously. Even in current space stations like the ISS, where there are resources and continuous support from Earth, small incidents can still become dangerous if not handled promptly, and that is in an environment where you can receive help in hours or days. When you extend the distance to light years, the concept of help almost completely disappears. This also applies to every other system on the ship, from navigation, engines, power sources, to radiation and thermal control systems. Every system has a certain failure probability, and when you have no ability to repair or replace from outside, you must carry everything you need from the start, which increases the mass. And as we have seen, mass is directly related to the energy required for acceleration. This is another loop, where preparing for every contingency makes the journey harder from the beginning. Even if you design the ship with very high redundancy, with many parallel systems and self-repair capabilities, you still cannot completely eliminate the possibility of an unforeseen failure, because in a complex system, the number of possible states is extremely large. And when the journey time stretches over tens, hundreds, or thousands of years, the accumulated probability of a serious failure approaches certainty. This completely changes the way you should think about risk, because you are no longer dealing with rare events, but with events that are almost inevitable. When you put all of this together, you begin to see that interstellar travel is not just going from point A to point B, but maintaining a perfect system in an unsupportive environment for an extremely long time, and just one small mistake or small incident can end the entire mission immediately, with no chance of recovery. This leads to a very direct but hard to accept conclusion. This is not a journey with backup plans, no plan B, no way to go back and try again, but a one-way road where everything must work correctly from the start and continue to work that way throughout the journey. And in a universe where every system has limits and every material has a lifespan, that requirement may not just be difficult, but unrealistic. The question that all of this leads to was posed in a very simple but profound way in 1950 by Enrico Fermi while he was having lunch with colleagues at Los Alamos. And he simply asked, "Where is everybody?" A question that sounds light but contains a great paradox. If you look at the numbers we talked about earlier, the observable universe contains about 100 to 200 billion galaxies. Each galaxy has hundreds of billions of stars, and many of those stars have their own planetary systems, meaning the total number of planets could reach a gigantic number far beyond imagination. Since telescopes like Kepler were launched in 2009, we have confirmed the existence of thousands of exoplanets, and the data shows that Earth-like planets are not rare. If you combine all of this, the probability that life has appeared in many places in the universe is very high. And if life can evolve into intelligence in one place, there is no clear reason why it should not happen elsewhere. This leads to a natural inference. If there are many intelligent civilizations in our galaxy, and if interstellar travel is feasible, then at least some of them should have developed technology to explore and spread. And in the billions of years of the galaxy's existence, we should have seen signs of them, whether probes, radio signals, or any other traces. But so far, every search effort, from projects like SETI that began in the 1960s to modern observations, has found no clear evidence of the presence of an extraterrestrial civilization. This silence, often called the Great Silence, is at the center of the Fermi paradox. If they could exist, and if they could come here, then why aren't they here? Many hypotheses have been proposed to explain this, from intelligent life being extremely rare to civilizations self-destructing before reaching interstellar travel capability. But one of the simplest and most consistent explanations with what we have discussed is that they cannot get here, not because they do not want to, but because the laws of physics do not allow it on any meaningful scale. When you put the barriers together, from the speed of light limit, the near infinite energy requirement, relativistic mass effects, radiation, collisions, navigation problems, journey time, and the complete lack of support infrastructure, you begin to see that interstellar travel is not just difficult, but almost impossible to carry out in the way we imagine. This means that every civilization, no matter how intelligent and advanced, may be trapped in its own star system, limited by distance and the speed of light in a way that has no realistic solution to overcome. And if that is true, then the silence we observe is no longer a mystery, but a natural consequence of the structure of the universe. Civilizations may exist everywhere, may develop, may reach high technological levels, but they remain isolated, like islands in an ocean too large to cross. Even communication is limited, because radio signals are also bound by the speed of light, meaning an information exchange between two civilizations hundreds of light years apart would take centuries for each reply, making communication unrealistic. When you look at the Fermi paradox from this perspective, it is no longer a question about the existence of extraterrestrial life, but a question about the ability to connect between civilizations. And the answer may be very simple but hard to accept. They are there, but distance and the laws of physics make meeting almost impossible. This also changes the way you view our position in the universe, because it suggests that the loneliness we feel may not be because we are special or unique, but because the universe is built in a way that civilizations cannot easily reach one another. And when you return to Fermi's original question, where is everybody, you may begin to see that the answer is not that they do not exist, but that they are too far, and the speed of light, which seems the fastest, is too slow to close that gap in any realistic time frame. When you push this logic even further, you reach a point where almost all debate ends, because it no longer depends on hypotheses or technology, but on the very fastest speed the universe allows. Light from the Andromeda galaxy takes about 2.5 million years to reach Earth, and that means when you see this galaxy in the night sky, you are not looking at it as it exists now, but as it existed at a time when the very distant ancestors of humans had not yet appeared. This is not an exception, but the general rule of the universe. All information, all signals, all interactions are limited by the speed of light, about 299,792 kilometers per second, and that is the absolute maximum speed that anything carrying information can achieve, according to the laws of physics we have verified. This means that not only objects, but also information, radio signals, light, and every form of communication are bound by the same limit. When you think about communicating with a civilization in another galaxy, you are not just talking about sending a message, but about waiting millions of years for that message to arrive, and millions more years to receive a response if there is one. At that scale, the concept of communication almost loses its practical meaning, because no civilization could maintain a dialogue lasting millions of years with such delays. And even on a smaller scale, within the same galaxy, distances of thousands or tens of thousands of light years still create delays large enough to make direct interaction unfeasible. What is important here is that you cannot overcome this limit in any way that has been proven, because all modern physical theories, from relativity to quantum mechanics, respect the speed of light as an uncrossable boundary for information. You can imagine hypothetical technologies, but until there is experimental evidence, everything we have points to the same conclusion. There is no faster path. This turns the speed of light from an impressive number into an absolute limit, a ceiling you cannot break. And when you place this limit next to the enormous distances we have discussed, you begin to see something very clear. Even the fastest possible speed is not fast enough to close the distances in any meaningful time frame. This affects not only travel, but also the way the universe is experienced, because you are always seeing the past, always receiving information late, and always separated from events happening far away. This is why the universe, even if it may be full of life, can still appear silent and empty from our perspective. Not because there is nothing there, but because what is there is too far for light to carry information to us in a time we can observe. And when you return to the question of travel, of a civilization coming from somewhere else, you begin to see that the problem is not how fast they can go, but how limited they are. If even light, which has no mass and is not hindered by the problems that matter faces, still takes millions of years to cross the distances between galaxies, then any object with mass, with all the additional limitations we have discussed, would be much slower. And that is the key point. If light cannot do it faster, then nothing can. This is not a hypothesis that needs further verification, but a direct consequence of what we have known and measured with very high precision for more than a century. When you accept this, you begin to see that distances in the universe are not just a big problem, but a fundamental structure, a property that shapes how everything exists and interacts. And in such a universe, crossing those distances is not just difficult, but may lie beyond the capability of any civilization, no matter how advanced. When you accept that even light is not fast enough to close these distances in any meaningful time frame, an unavoidable consequence begins to emerge. If no one can get here, then every civilization in the universe is isolated within its own region of space. This is not a choice, not a strategic decision, but a direct result of the physical structure we have discussed, where distances are measured in light years and the maximum speed is locked at a fixed value. You can imagine millions, even billions of civilizations scattered throughout the Milky Way, each developing, evolving, and asking questions similar to ours, but all separated by distances for which there is no realistic way to cross. This distance is not just large in arithmetic terms, but creates an almost absolute separation, because it not only prevents physical travel, but also makes communication unrealistic. A radio signal sent out may take hundreds or thousands of years to arrive, and the reply, if there is one, also takes the same amount of time to return, meaning any conversation would be stretched far beyond the lifespan of an individual, even beyond the stability of a civilization. What is important here is that this isolation does not depend on the level of technological progress, because every civilization, no matter how advanced, must obey the same physical limit. You may have greater energy, better machines, higher intelligence, but you still cannot exceed the speed of light, cannot shorten distances, and cannot avoid all the barriers we have analyzed. This means that even a civilization that reaches the level of harnessing the entire energy of their star is still trapped within their star system in a practical sense. And when you think about that, a possibility begins to appear. We may never meet one another, not because there is no one else, but because the universe does not allow us to connect in the way we desire. You can look up at the sky and see billions of stars, knowing that each star may have planets, each planet may have life, but all of that exists like islands in an ocean too large to cross. This is not an easy conclusion to accept, because it goes against our intuition and hope for exploration and connection. But it fits in a surprisingly consistent way with everything we have learned about physics. And when you place this next to the Fermi paradox, the silence of the universe is no longer a mystery that needs to be explained with complex hypotheses, but becomes a natural consequence of distance and speed. The universe may be full of life, may be full of intelligence, may have civilizations that have existed for millions of years, but all of them remain isolated, not because they want to, but because they have no other choice. And that leads to an idea that is both astonishing and thought-provoking. The universe may be more crowded than we ever thought, but at the same time lonelier than we ever imagined, not because of a lack of life, but because of a lack of ability to connect between those forms of life. What makes this conclusion hard to accept is not a lack of data, but the way we are accustomed to thinking about the world, because humans tend to take our experience on Earth as the standard to infer how the universe works. On Earth, if you want to go from point A to point B, you just need a faster vehicle, a better road, or more time, and sooner or later you will get there. That intuition is so deeply ingrained that we apply it to every scale, even when it no longer holds. Movies and science fiction have reinforced this for decades, from stories about interstellar travel in a few hours or days, to ships that can jump through space almost instantly, creating an expectation that distance is just a technical problem yet to be solved. But when you return to the real numbers we have gone through, from 4.24 light-years to Proxima Centauri, to 100,000 light-years for the Milky Way, to 2.5 million light-years for the Andromeda Galaxy, you begin to see that the going from A to B model no longer applies. The problem is not that you need a faster car, but that the distance is so large that even the fastest possible speed is not enough to create a meaningful journey. This is where your intuition really fails, because it is built on linear changes, where doubling the speed halves the time, but at cosmic scales you are facing exponential differences, where increasing speed a little does not change the nature of the problem. A simple example is that you may think, if we go 10 times faster than Voyager 1, the journey would become reasonable. But when you calculate, you realize that instead of 70,000 years, you would still need 7,000 years to reach the nearest star. And 7,000 years, 0,000 years, is still a time span far beyond any social or technical system we could maintain. This shows that the problem is not that we are not fast enough, but that we are misjudging the scale of the problem. Science fiction often ignores or compresses these numbers to tell an engaging story, and that is perfectly reasonable in an entertainment context. But when you bring those expectations into reality, you begin to see a large gap between what you think is possible and what is actually allowed by physics. This does not mean science fiction is wrong, but that it operates in a space where limits can be temporarily ignored, while reality does not. When you return to the data, to the measurements, to what has been verified for over a century, you see a very consistent picture. The speed of light is the limit. Distances are enormous. Energy is a barrier. And all these factors combine in a way that does not allow a simple solution. The problem is not that we lack information, because we have measured the speed of light with high precision, observed galaxies at distances of millions of light years, and verified relativistic effects in the laboratory. The problem is that our intuition cannot keep up with what the data is saying. When intuition and data conflict, the natural reaction is to trust intuition, because it is what you feel. But in science, it is the data that you must trust. And when you truly accept those numbers, not just understand, but accept their meaning, you begin to see that many ideas we take for granted, like a civilization easily traveling from one star to another, are not actually based on physics, but on the way we are used to thinking. This is the point where you need to adjust your perspective, because the universe does not work the way we want, but the way its laws dictate, and those laws do not care about our intuition. So when you ask why we have not seen aliens, or why we have not gone to the stars, the answer may not lie in us not being smart enough, or not having enough technology, but in us having misjudged the problem from the start. And when you correct that view, many things begin to become clearer, not easier, but at least consistent with what the universe is actually doing. Putting everything we have gone through together, from distance, speed, energy, radiation, collisions, navigation, to time and isolation, you begin to see that they are not separate problems, but different manifestations of the same deeper reality, physical limits. Every time you try to solve one of those problems with a technical solution, you immediately run into another limit, and ultimately all of them lead you back to the same point. The laws of nature do not allow you to overcome these barriers in the way you desire. This is the most important thing to understand, because it completely changes the nature of the question. If this were just a technical problem, then you could say that with enough time and creativity, we would find a solution, just like we have done with thousands of other problems in history. But when the problem is at the level of physical laws, then no level of technological progress can overcome it, because technology itself must obey those laws. You can improve efficiency, optimize systems, find smarter ways to use energy, but you cannot create infinite energy. You cannot make objects with mass move faster than light, and you cannot completely eliminate interactions with the surrounding environment. This applies not only to us, but to any civilization in the universe, even if they are thousands or millions of years more advanced than us. A civilization may harness the entire energy of their star, may build structures we cannot yet imagine, but they are still bound by the same equation, the same constant, the same speed of light limit that we have measured. This is what makes this limit special, because it is not a local or temporary barrier, but a universal limit that applies everywhere, at all times in the universe. You cannot go somewhere else and hope that the physics there will be easier, because every observation we have from distant galaxies shows that the laws of physics are consistent across the entire observable universe. This means that any civilization, whether in the Milky Way or in a galaxy millions of light years away, must face the same problem and the same limit. When you look from this perspective, the question about interstellar travel is no longer when will we be able to do it, but becomes, is it within the realm of what is possible at all? And with what we know now, the answer seems to lean toward no. This does not mean we cannot explore the universe, because we already are doing so through telescopes, probes, and indirect observation methods. But it does mean that physically traveling those distances on a large scale, with humans or even with complex systems, may not be a realistic option. This also does not diminish the value of science or our curiosity, but on the contrary, it makes understanding and accepting these limits an important part of knowledge. Science is not only about finding what can be done, but also about recognizing what cannot be done, and clearly distinguishing between the two. When you accept that there are limits that cannot be crossed, you are not giving up on exploration, but only adjusting the way you explore, focusing on what lies within the feasible range. And in the context of interstellar travel, that means instead of trying to overcome the laws of physics, we need to understand that those very laws have shaped how the universe works. And within that framework, Physically traveling the vast distances between the stars may not be a path that any civilization can take. This is not a pessimistic conclusion, but one based on what we have measured, verified, and understood about the universe, and it leads to an important realization. The limits do not lie in our imagination, but in reality itself. When you return to the starting point of this entire story, the seemingly simple idea that light is fast, you begin to see it in a completely different way, because fast only has meaning in a certain context, and when you place it in the scale of the universe, it is no longer fast, but becomes a limit so slow it is astonishing. Light can circle the Earth more than 7 times in 1 second, but it still takes more than 4 years to reach Proxima Centauri, and 2.5 million years to travel from the Andromeda Galaxy to us. And that tells you that the problem is not in the small speed, but in the distances being too large. When you synthesize everything we have gone through, you see a chain of tightly linked barriers. Distances between stars measured in light years. The energy required to accelerate approaching infinity as you approach the speed of light. Effective mass increasing and making acceleration progressively harder. Radiation and collisions turning space into a dangerous environment. Navigation requiring almost absolute precision in a system with always delayed information. Journey times stretching far beyond the lifespan of any system, and complete isolation, making every error irreparable. None of these factors exist in isolation, and you cannot solve them one by one in a linear way, because every solution you propose for one problem only worsens another. This leads to an important conclusion that many people do not want to accept. The problem is not that we are not smart enough or not developed enough, but that we are facing limits built into the very structure of reality. You can imagine a civilization millions of years more advanced than us, capable of harnessing the entire energy of their star, with technology far beyond anything we know, but they would still have to obey the same speed of light, the same ELMC-Quero equation, the same time dilation effect, and the same physical environment. That means if we are limited, they are limited too, not because they lack capability, but because there is no way to overcome those limits without changing the laws of the universe themselves. When you look from this perspective, the question of whether there are other civilizations out there becomes less important than the question of whether they can get here. And the answer seems to be that they cannot, at least not in the way we usually imagine. This also brings a new perspective on the silence of the universe, because it suggests that this silence is not a sign of emptiness, but a sign of distance and limits. Civilizations may exist everywhere, may be looking up at their own skies and asking questions just like us, but all are trapped in their own islands, separated by an ocean that cannot be crossed. And this is where you begin to see a deeper idea about how the universe is structured, not as a place designed for easy movement between points, but as a system where distance is a fundamental property, where everything is dispersed and separated. The universe does not prioritize taking you from one place to another. It prioritizes keeping those places far apart, and the speed of light is the mechanism that ensures that. When you accept this, you begin to understand that interstellar travel is not just an unsolved technical challenge, but maybe something outside the realm of what is possible with current physics. And that leads to a final thought, a thought that is not comfortable, but very consistent with what we know. The loneliness we feel when looking at the universe may not be an accident or a temporary phase, but a natural consequence of the laws of physics. Not because there is no one else, but because no one can reach anyone else. And in a universe where light, the fastest thing we know, is still too slow to connect the points together in any meaningful time frame, isolation is no longer the exception, but the default state. If you find this perspective changes the way you understand the universe, please subscribe to the channel so you don't miss the next in-depth scientific analyses. See you again in the journeys of exploration, where the truth may be simple, but not at all intuitive.